Hi everyone, welcome to Vedantu J English. I'm Diksha Kaushal, your chemistry master teacher. So everybody do let me know in the chat box if I'm clearly visible and audible to all of you or not, so that we can start with the session. And today we are going to do ionic equilibrium, right? So till now we have done chemical equilibrium that forms the base of ionic equilibrium, and today we are going to start with ionic equilibrium, where as you can see on the thumbnail over here, ionic equilibrium will learn about acid base, right? How acid base, what are the theories given for acid and bases, right? Then you'll understand what is Ka and Kb, what is Kw, what is pH, calculation for pH of acid bases pairs, like strong acid, strong base, weak base, two strong acids, two strong bases, one strong acid, one strong base, one weak base, and strong acid and weak acid, and weak base and strong base, right? And two weak bases. So all these things we are going to do today. So everybody do let me know if you all are ready for this one, and full concentration is required here, right? I hope to complete all of this today, but otherwise it's not like I'll complete this lecture within 2 days or 3 days. I'll see what is the sequence going on. The major part is you should be able to understand it, but the target is to complete all of this today. That will be great, right? Okay, yes everybody. Okay, Vedic, Rajkumar, Chandu, Pukiri, Deva, Deepa, Sanjay, Little Queen, alone. Boy, why you are alone? Why so much alone that you have put your name as a lone boy? What's the thing going on, guys? Yes. And also don't forget to hit the like button over there, because that motivates me to do more better for you, right? Okay, and it doesn't cost anything. It's totally free to like the button, right? It's totally free. Now let's see this. Yes, students, let's see this over here. Excited to start ionic equilibrium. So if you see ionic equilibrium, right, here ions are involved, dissociations we talk about. The type of equilibrium involving ions in aqueous solution is called as ionic equilibrium, right? Now here we'll talk about in which equilibrium involving ions in the aqueous solution. So basically here you have a, like, let's say two ions are combining to give a compound, or one compound is being dissociated into ions. That is an equilibrium that is established between them is called as ionic equilibrium. Now if you see what is as, first we will talk about acid and bases, then we will talk about strong acid and strong bases, weak acid and weak bases, right? The definitions should be clear before moving towards the pH calculations, right? So here first thing is Arrhenius based. Now first theory is given by Arrhenius. Arrhenius based acid and bases. Arrhenius, what he told us about acid and bases, let's talk about that. Arrhenius dissociates in water to give. Arrhenius said that acid dissociates in water. That acid will dissociate in water to give H positive ions, right? That when you put acid, any acid in water, it is going to give you H positive ion. And base is in water, it is going to give you OH negative ions. So he is not saying that acid gives H positive, bases gives OH negative. He is saying acids in water gives H positive and bases in water gives OH negative. For example, here you will see in this case HX, right? It dissociates into H positive and X negative in aqueous solution. NaOH, which is a base, it dissociates into Na positive and OH negative, as we can say that it is a base. Then there comes Bronsted, Lowry acid and bases, right? Now why it is so? Because there were so many bases, like you talk about ammonia, NH3. Now in case of ammonia, how can you say that ammonia, ma'am, is a base? Ammonia does not give you OH negative, right? If I talk about ammonia, NH3 does not give, or you can say does not have OH negative, right? It does not have OH negative. So what we do now? Now then there is a concept called Bronsted-Lowry concept of acid and bases. In this case, he said that acid are proton donors, right? That acids will donate protons and bases are proton acceptor. He made a new concept that is not related to OH negative and all of that. He just said acid are proton donors, they give protons, and bases are proton acceptors. For example, you have any acid, right? Like this acid, this acid, this acid, this acid, they will give protons, they will give H positive. And if you talk about NH3, that is a base, it is going to accept lone pair of, because see, ammonia here, nitrogen has these lone pair of electrons, okay? It has these lone pair of electrons, and because of these lone pairs, it is going to accept H positive from the water, and it is going to get converted to ammoniated ion, right? Okay? That is the reason this is called a base, right? Then there comes a concept of Lewis acid and Lewis bases, but before that, a very important thing that you must know, the concept of conjugate acid and conjugate base. What is the concept of conjugate acid and conjugate base? Let's talk about that. If I say there is an acid that donates H positive, then it is converted to conjugate base. It gives H positive after that. And if you talk about a base, it accepts H positive and it is converted to conjugate acid. And it is converted to conjugate acid, right? Now, if you see this over here, acid, this is converted to conjugate base and H positive. This is base, it accepts, it is converted to conjugate acid. Now, what is, like for example, you have HF, right? It loses H positive and it is converted to F negative. Now, this F negative is a conjugate base and this is an acid and this is an acid. Now, always remember that if your acid is strong, then conjugate base will be weak. If acid is weak, then conjugate base is going to be strong. They are always opposite to each other. For example, I am saying that acid is strong. If this acid is strong, then here this is going to be a weak conjugate base. I'll think, ma'am, how you can say that? Okay, let's see one thing. If I am saying that this acid is very strong, that means this acid is like, I want to donate H positive. I don't want this H positive, bro. I want to donate it. Okay, donate the H positive, right? So he is very eager to donate H positive, right? If you're like, gosh, thank God H positive is donated, would you want to accept H positive again? This fluorine is like, I want to donate, I'm such a, वैसे HF is not a strong acid, so I'll write HCl here, right? Then it will become wrong. Let's say I'm writing HA. Okay, I'm writing HA because we are talking about strong and weak both. Then I'll also tell you the examples of strong and weak. Right now, just focus. If this is strong, this wants to donate H positive, then it would never, when it has finally donated H positive and getting converted to A negative, it would never want to accept H positive. That means this base does not want to accept H positive. The base which is not willing to accept is a weak base, right? And similarly, if this is weak, if there is a weak acid, then the conjugate base is going to be very strong. The reason is, ma'am, because here it is like, I don't want to donate. Then finally it has donated. You forcefully make it donate. Now it is A negative. It's like, I never wanted to leave it, but you have forcefully done it, so it will go back and it will accept. When it is accepting, that means it's a very good base that wants to accept H positive, right? So that's why it is opposite, right? And similarly is the case of base here. Let's say there is a base, right, which accepts H positive and it is converted to BH, right? Then we say that this is a base, right, and this is the conjugate acid. Now we say that if this is strong, similar lines, then this is weak. If this is weak, then this is strong. Okay, right? Tell me, is that clear? Now let's understand Lewis acid and Lewis bases. This is the best theory of acid and bases because all the acids, bases, all the examples, right, you can cover in Lewis acid and bases definition. So Lewis acid and bases states that Lewis acids are electron deficient, right? Acid accepts electron pair. Now it doesn't matter from whichsoever situation it is accepting. Acids are, it is not saying hydrogen acceptor. It is saying bases are electron acceptor. Acids are electron acceptor and bases are electron donors, right? That means we can say a Lewis acid is electron deficient. Whenever it is deficient, it wants to accept the electrons, right? And bases are electron donors. That is why they are electron rich. They are electron rich. Now if you see an example here, there is let's see the examples: AlCl3, BF3, right? These are the examples of acids because aluminium and boron, they are electron deficient. They don't have complete octet. Talk about ammonia, here it has lone pair. Phosphorus, if you see, it has lone pairs, right? So these are bases, right? Now you can also write it like this. Wait a minute, you can also write it like this. Yes, you can also write it like this, that Lewis acids, I'll just write here, Lewis acids, and here I'll write Lewis bases, Lewis bases, bases. Now if you see, if you talk about Lewis acids, right, what are these Lewis acids? Lewis acids are actually electron deficient. That is why they will have vacant orbitals, or they will be cations, or they can be cations, right? They can be electron, there is vacant orbitals or cations, right? These are incomplete octet, or you can also say incomplete octet, like boron has incomplete octet. All these are Lewis acids, right? Then you talk about Lewis bases. In Lewis bases, what you have, everybody? In Lewis bases, what you have? In Lewis bases, they are electron rich, right? If they are electron rich, then we can say they are negatively charged, right? They are not positively charged, they are negatively charged, right? Or and then you can say they can have lone pairs, or they can have multiple bonds, right? So these are the examples of Lewis bases, right? Everybody tell me, is that clear? Yes, that works. Everybody do let me know in the chat box, right? Okay, now let's talk about two category of electrolytes. Electrolytes are of two types. Firstly, there are two things. One is electrolyte, other is non-electrolyte. Electrolyte is that substance which is dissociated into ions, right? And non-electrolytes are not at all dissociated. For example, you have glucose, urea, yes, Glucose, urea, fructose, all these are not dissociated into ions only. That's why we will not discuss non-electrolytes in ionic equilibrium. You are going to discuss electrolytes only, because ions you need, right? So electrolytes we'll discuss. So electrolytes are of two types. One is strong, other is weak. Strong electrolyte is the one which has 100% dissociation, like literally 100% dissociation. If you have 100 molecules of HCl, right? Then after dissociation, 100 molecules of H positive and 100 molecules of Cl negative, you will have totally all the ions will be dissociated here, right? But if I talk about, this is about strong electrolyte, right? But if I talk about weak electrolyte, then maybe you have 100, let's say 100 HF, right? Let's say this is a very common weak electrolyte, CH3COH, right? Now maybe you have 100 initially, maybe out of that 30 are dissociated. You have 30 CH3COO negative and you have 30 H positive, but rest of them 70 are as it is. They are as it is, they are not at all dissociated. That means out of that total chunk, right, only some of them are dissociated, right? Okay, right, everybody? It's like you have 10 dosas, right? And out of that 5 dosas you cut it into half and distribute it in the family members, and 5 dosas are as it is full. Now that is not 100% dissociation. 100% dissociated is when you have when you have 10 dosas, you dissociate all of them into two halves, and then now it will become 20 dosas because you have cut it into half, right? So that is the case. Now based on strong electrolyte and weak electrolyte, let's understand this. Which are strong electrolytes, which are weak electrolytes? Because if you understand this only, then you'll be able to apply where to apply which formula, right? Okay. Now if you see strong electrolytes, these are like salts you have, right? Salts, all the salts that you have are strong electrolytes, right? Then strong acids, now this is a very important thing, right? Acids like H2SO4, right? H2SO4 is strong, but H2SO3 is weak. Okay, remember that. H2SO4. Now here I have written strong acids and weak acids. These are weak acids, these are weak bases. These are strong acid, these are strong bases. So H2SO4 is strong, H2SO3 is weak. HNO3 is strong, HNO2 is weak. One oxygen I am subtracting. HClO4 is strong, HClO3 is also strong, but HClO2 is weak, right? Then you have HCl, HI, HBr are strong, but HF is weak. Then HCN is weak. Oxophosphoric acid that we have done in P block, that are all weak acids, right? Carbonic acid, H2CO3 is a weak acid. Boric acid, right? H3BO3, that is a weak acid. All the organic acid, carboxylic acid, these are weak acids, right? Okay. Now what about bases? When we talk about strong bases, alkali metal hydroxide. Alkali metal means you can say group number 1, right? Lithium, sodium, potassium, rubidium, French. All of their hydroxides are strong base. They are strong base. So alkali metal hydroxide plus BaOH twice. This is very important, that group number 2 hydroxides are weak. Alkaline earth metal, all of them are weak except for BaOH twice, that is in the category of strong. So that is very important, that group number 2, that is you can say calcium, magnesium, beryllium, in barium you can skip. right? So all of these have weak hydroxide, but barium has strong. Then NH4OH, 1 degree, 2 degree, 3 degree amine, all the organic bases, they are weak. Right, everybody? Yes, good Nishni. Yes, Chyan, tell me. Clear? Now let's see the next one here, right? Okay, sure, Shiva, right? So now let's talk about, now the interesting part is going to start, right? And you're going to enjoy this because, you know, uh, see, ionic equilibrium, if you see this like, oh my God, right? As compared to chemical equilibrium, more conceptual knowledge is needed. It's not like you can cram everything here, right? You need to understand things in ionic equilibrium. You need to understand the formulas. You need to understand where to apply which formula. You also need to understand the derivations here, right? Because sometimes, you know, derivations, because in the question they will not give you apply this formula of pH, and around 15 formulas, 15 to 20 formulas of pH only you will see here. Only pH calculation formulas, around 15 to 20. I'll show you more than that as well, right? So many formulas of pH calculations are there. Firstly, to learn those formulas, I'll give you a simple way of understanding and learning those formulas, right? Second thing is how they are derived. We'll talk about that, so that by chance you forget this in your exam, even then you can solve it, right? Okay, yes. Now firstly, let's talk about dissociation of weak acids and weak bases, right? So dissociation is going to be same in all the cases. Let's see, I'm going to do the same thing. Now tell me one thing. Firstly, I'm taking acid as concentration, I'll always take as C, okay, right? Initial concentration, I'm taking it as C. Now, if you remember yesterday, in the yesterday I'm saying in the chemical equilibrium last class, I told you about dissociation. So what I told you, at equilibrium it will be initial minus initial into alpha. Now this term will be multiplied in the, this term will be as it is there in the product side, that is C alpha, and this is C alpha. Right. Then the next question is, ma'am, why, ma'am, it is an acid, ma'am, it is getting dissociated in water, then why it is giving this H3O positive? Why not H positive? So remember one thing, what will happen, the lone pair of water over here, this is water, the lone pair here will accept H, right? This will become H2O positive, it will become the hydronium ion, right? It will become the hydronium ion. So H positive concentration is equals to H3O positive concentration. More H positive are released, those H positive are going to link to H2O, and those many hydronium ion will be produced here. So you don't need to worry about that. Either you write H positive or you write hydronium ion, that is the same thing, right? Then if you see, this is equilibrium concentration. Now this water, it is a pure liquid, and if you remember, for pure liquid concentration is taken, we don't include pure liquid in the equilibrium constant value, because here we are talking about acid. So for acid we have Ka, that is the dissociation constant of acid, right? So Ka is equals to product is what, H positive, or hydronium you can write X negative, divided by Hx, right? Now liquid you want right here, this is C alpha into C alpha divided by this is C minus C alpha, so it will be C square alpha square C1 minus alpha, so it will cancel out, so it will become C alpha square 1 minus alpha, right? That will be the full derivation here, right? Okay, because in most of the books you will see C only as taken as the initial concentration, so that's why it is by convention we take C. You can take X, Y, Z, whatever you can take by convention, because C means concentration, that's why we have taken it here, right? Because most of the formulas are regarding this only, right? Okay, so that's why C I have taken, right? Achha, now see one thing, Ka is going to be C alpha square 1 minus alpha. If alpha is very small, it is even smaller than 0.05, then it is also by convention it is said that if it is even smaller than 0.05, then 1 minus alpha, this alpha is so small that it is ignored in front of 1, so that's why it becomes approximately equals to 1. That is the reason your new formula will be Ka equals to C alpha square, and this will be the value of dissociation constant. Tell, is that clear, everybody? What is the value of dissociation? Why the students are not interested in ionic equilibrium? I don't understand. Huh? Why the students have not joined the class? Tell me. I don't know. Don't you want? Wait a minute. Let me just see why the students have not joined. I mean, guys, what to do? Okay, ma'am, chapter hard. It's not hard, yeah. It's actually easy only. I was about to make this easy for you, but you are making it difficult for me to teach. Right? K is equals to C alpha square. Tell me if this particular slide is clear to all of you. Right? Because we are going to repeat this thing again and again and again. Right? We take initial as C. This is 0. This is 0 initially. C minus C into alpha. C alpha will be as it is. Then you take the Ka value as we understand it in chemical equilibrium as well, product by reactants. Put in the values, 1 minus alpha is approximately equals to 1 and K is equals to C alpha square. Right? Okay. Now the equilibrium constant for dissociation is defined as this, that is Ka, and that we have defined as Ka is equals to C alpha square. That is your formula of Ka, right? Now, next thing is H positive concentration. So if you can see this over here, can you see what is the value of H positive concentration? H positive or the hydronium ion. What is the value of hydronium ion? That is C alpha, right? So now I'll put the C alpha value here, right? C. H positive is equals to C alpha, that is there. Now I'll put this here. Alpha I need to calculate, so alpha I'll calculate from here. Alpha square is equals to Ka by C, that is Ka by C. So we can say that, alpha equals to under root of Ka by C, right? Now I'll put this value under root of Ka by C, put alpha is equals to under root Ka by C here. What you will get here? You will get is H positive concentration equals to C into under root of Ka by C. I'll take say C inside, it will become C square Ka by C, C will cancel, and this will be under root of Ka, this is very important, Ka into C, right? So you can write this over here, the formula becomes H positive concentration is equals to under root of Ka multiplied by C, and that becomes your H positive concentration. Tell me if that thing is clear to all of you or not, right? Okay, H positive concentration, how it is coming out to be under root of Ka multiplied by C, right? Okay, yes. Notes you will get in the PDF, don't worry about that, right? Notes you will get in the PDF. Now tell me if that thing is clear. What we have here, we have the value of Ka. You have calculated this thing, so I'll just recap what we have done. It's very smooth. If you see this, it's, you don't have to remember as such anything. Just this thing is the major part. After this, I have just applied the definition of Ka, that is product by reactants. Put it here, you will get Ka is equals to C alpha square. Then calculate the value of alpha, that is under root Ka by C. Then we know that from here H positive concentration is nothing but it is C alpha, right? So we'll put the value of alpha is equals to under root Ka by C over here, and you will get under root of Ka into C as the H positive concentration, right? Then what you have, this, if I say, let's say you have two acids, right? You have two weak acid. Let's say that we have two weak acids with Ha and Hb. Now if I say that for one weak acid, here the concentration is, here the H positive concentration is H positive of 1, here the concentration is H positive of 2, right? Here C1 is the initial, here C2 is the initial. Here you can say yes. Here I am taking the dissociation constant as Ka1, here it is Ka2. So I can say that H positive of 1 is equals to under root of Ka1 into C1. H positive of 2 is equals to Ka2 into Cu2. When you take the ratio of both of them, it will become under root of Ka1 C1 divided by under root of Ka2 C2, right? Then you take that for the acids having same initial concentration. If I say initial concentration, that is represented, what is initial concentration? If you see this here, what is the initial concentration that you have taken? You have taken initial concentration as C. For, let's say for Ha it is C1, for Hb it is C2. So if initial concentrations are same, then I'll say that H positive of 1 is equals to 2. These two things will cancel each other if they are same. So it will become H positive of 1 by H positive of 2 is equals to under root of Ka1 by under root of Ka2. Right? Okay, tell me. This you don't have to remember. You don't have to remember this. You don't have to remember this, right? You don't have to remember this. It is just that if they ask you the ratio, then you're going to do this, right? If initial concentrations are same, then the H positive concentration ratio is equals to under root of their ratio of dissociation constants, right? But here what you need to remember is, because these derivations you can't do again and again, so one thing I am marking it in a red box, okay, what you have to remember. So this is what you will remember, whatever I have marked in red box, that you will remember. Ka is equals to C alpha square. This is the first thing, that formula should be on your tips. Then you must remember that H positive concentration is equals to under root of Ka into C, right? H positive concentration is equals to under root. This is very important formula, right? And then this is a very important formula, right? Okay, right, everybody? Now let's see dissociation of weak acids. In this, if I say, now remember in P of anything, now this is applicable everywhere, that P of anything means anything. You put here P of dosa, it will be equals to minus log of that anything. So if you put P of dosa, right, P of dosa, that will be equals to minus log of dosa, right? So whatever you put, P of Diksha Ma'am is equals to minus log of Diksha Ma'am. P of Shrey, P of Shrey is equals to minus log of Shrey. Whatever you put here. So here if I am putting P of Ka, that is equals to minus log, and here base 10 we are using log of base 10 of Ka, right? This is also another formula that is quite important, right? Then we say that since the values of Ka are generally very small, a separate quantity is defined also, that is pKa, and always remember that pKa, if you want to define the acidity, more is the acidity, more will be the value of Ka, and less will be the value of pKa, right? always they are whatever in this chapter I have marked in red box, that is important for you. Acidity, if something is a very good acid, it will have very strong Ka value and its pKa value will be low, right? Okay. Now see this thing, for example, if for an acid Ka is equals to 10 raised power minus 5, so pKa will become equals to minus log of 10 raised power minus 5. So whenever you solve this particular value, one thing to remember here, that whenever you have minus of log base 10 of something, the power comes in the front. So what you will say, minus of minus 5 log base 10 of 10, and log base 10 of 10 is nothing but 1. Why log base 10 of 10 is 1? Because always remember this properties, these properties I am writing side by side, okay? These properties I am writing side by side with yellow pen, okay, over here. So I'll just write the properties with this pink pen over here. That is log x of x is always 1. If I say log dosa of dosa is equals to 1. So any log you have, if the base is 1, then it is going to be 1. If the base and the value is same, then its value is going to be 1. So when we say log of base 10 of 10, that is 1, right? So it will be 5 is the correct answer. So this is the value of pK. We can say that from the expression of pK, it is clear that as Ka value increases, pK value decreases. Why it decreases? You can also do one thing here. Let's calculate. This is for pK for 10 raised to power minus 5. Let's calculate the pK value for 10 raised to power minus 2. Okay, let's see which pK value is greater. Let's see which pK value is greater. So here it is pKa minus of log 10 raised to power minus 2. Now this is minus of minus 2 log base 10 of 10. That is 1, so it is going to be 2. So log pKa value is going to be 2. Can you see one thing over here, that Chayan, this is an English channel, right? When there is a Hindi channel, I'll talk in Hindi, right? If it is an English channel, I'll talk in English. If it's a Tamil channel, I'll talk in Tamil, Telugu, right? So that you have to see. Okay? Okay, whatsoever is the language of the channel, whatsoever is the audience, I'll talk in that, no? Then we would have written here Vedantu JEE Hindi, right? But it's English. So I'll talk in English, right? Okay. So if you see 10 raised to power minus 5 in this, which one is greater? Obviously, this one is 10 raised to power, this one is greater. 10 raised to power minus 2 is a more greater value. Ka of this one is greater, but pKa of this one is less. That means they are inversely proportional. Lesser the value of pK, stronger is the acid. The one that I have told you, that you can write here, that acidity is directly proportional to Ka and it is inversely proportional to pK. Okay, understood? Yes. Done, done. Yes, everybody? Tell me. Tell me, students, if that is clear. Right? Then we have the same thing for base. Now, when we do it for base, now it will get more easy for you. Right? It will get more easy for you because we are going to repeat it. Right? So, the revision will be side by side only. So, you don't have to remember base as well because it is same. Just replace Ka with Kb, OH with H positive, like all these things. So here if you see, this is C, this is 0, initially it is 0. This will become C minus C alpha, this will become C alpha, this is C alpha, because in degree of dissociation it is initial minus initial into degree of dissociation. Then this quantity that you have subtracted here will be added here with the stoichiometry. Stoichiometry is 1, so it is 1 into this value. It is 1 into this value, right? So that is how I am writing this. right? I am also telling you how I am writing this. Now the equilibrium constant for dissociation of bases is defined as Kb. That is nothing but it is M positive and this is OH negative divided by MOH. Now, ma'am, why you have not written water? Because it's a pure liquid. And the concentration of pure liquid, we never write in the pure liquid or pure solids are never written, right? Okay? Yes? I don't... This though you are asking me, ma'am, why you are a girl? Ma'am, why I am a boy? Ma'am, why I am was born as a boy? Ma'am, why you are born as a girl? Right? Weak acids, why they don't dissociate? That is a property of weak acid that they don't dissociate. That is how scientists have classified that some of the acids were getting 100% dissociated. So they named it strong acids. Some of them were not getting dissociated. They are non-electrolytes. Some of them were dissociated to small extent or maybe not 100% dissociated. They named it weak acids. Okay? So here it is M positive OH negative divided by this. What is M positive? Tell me about it. M positive, see, this is C alpha. Again, same thing will do. C alpha multiplied by C alpha. This is C minus C alpha. C square alpha square divided by C1 minus alpha. C will cancel. This is C alpha square divided by 1 minus alpha. And if I say what I am writing, if alpha is very less than 0.05, then we can say, as we have written there as well, Kb is equals to C alpha square, and that one is your formula that you must remember, that Kb is also equals to C alpha square, right? Okay, this is the degree of dissociation for weak bases. Maybe it can be 20, 30, 40, 50, any percentage, but not 100%, right? Okay. Now, on the similar lines, we know that what is OH negative? Its concentration is C alpha. On the similar lines, we can calculate the value of alpha here. See, if Kb is equals to C alpha square, then alpha is equals to under root of Kb by C. So you put it here, right? You put it here, and then what you will get here, you put it here, and then what you will get here is this thing. This is OH, oof. This is OH negative is equals to C into, this is Kb divided by C. You just take it inside, it will become Kb into C square. This is C, it will cancel out and this will become C into Kb, right? That will be the answer. If you remember, same answer was there for weak base. So that is the interesting part of ionic equilibrium, that the formulas, the interesting and the difficult part is that the formulas are so similar that we end up doing mistakes, right? That's why to understand that why it is this, why it is this, that is very important, right? So OH negative is equals to under root of Kb into C, right? Kb into C, that is your another formula that you must remember, right? That you must remember, right, everybody? So now let's see similarly like we did in weak acids. For first, we have taken two weak bases. One weak base is this, where concentration is C1. Here initial it is C2. Here it is Kb1. Here this one is Kb1, Kb1. This one is Kb2, right? And if you see here, it is, we are defining the OH negative of 1. This is OH negative concentration is for second base, right? When you divide it, because OH is equals to, because if you know that OH negative is equals to under root of C into Kb. So for OH1, it is Kb1 into C1. Wait a minute. This is Kb1, this is Kb2. Okay, this is Kb1 into C1, Kb1 into C1. ठीक है, Kb1 into C1, Kb1 into C1, this is Kb2 into C2. You take the ratio here, that will become this. If I say both the initial concentrations are same, then this will become OH of 1 divided by OH of 2 will be Cc will cancel, and this will become under root of Kb1 by Kb2. That means we can say this over here, more the value of Kb, stronger is the base. That means this generalization we can say that basicity and Kb value are directly proportional to each other. Basicity, just like acidity is directly proportional to this, basicity is directly proportional to Kb. That is there. Right? Now, like we defined pKa, here we will define pKb. Right? So let's see. pKb, tell me pKb is equals to minus log base 10 of Kb. What I told you, pH of P of anything, if it is, let's say P of X, that will be equals to minus log of X. So here this X is Kb. So P of Kb is equals to minus log of Kb, right? That is the formula always. Now, when you solve this for two different Kb values, right? Let's take an example. I'll solve it for 10 raised to power minus 4. Let's solve it for two values, okay? I'm solving it for two values. That is, let's solve it for Kb is equals to 10 raised to power minus 3 and Kb is equals to 10 raised to power minus 7, right? Here pKb is equals to minus log of, so you must know the value that is here will become pKb. So for pKb is equals to 10 raised to power minus 3, 3 will become the pKb value. But still, if you want to solve it, this minus of 3, and this is log of base 10 of 10, that is 1, so it will become 3, right? So on the similar case, I would just say, just remember this thing, I'm writing it here. Just remember one thing, that if X is equals to 10 raised to power minus X, minus, if A is equals to 10 raised to power minus X, then log of A is equals to X. Okay, just remember this thing. Okay, you don't need to do this again and again. In exam, you will not do these things, right? So just directly you should be able to see that, okay, if they have given the value of Kb, then I can easily say what is the value of pKb, right? So applying this thing here, if Kb is 10 raised to power minus 7, then log of Kb is just this 7. So you can write this here, P log of Kb I have written, P of A, right? P of A, right? So you can just write this, right? So P of that Kb is equals to 7. Now you can see this, the Kb value of this one was greater, but the pKb value of this one is greater, right? That means we can write one more thing over here, that basicity, you can just see this here as well, that basicity is directly proportional to Kb, which is inversely proportional to pKb, right? Okay, tell me, is that clear, students? Is that clear? This is also important, right? What happens if two weak bases are in same solution? Can we add OH contribution individually? We'll talk about that. Two weak bases, all these are different cases. These are different cases that we'll talk about, right? That when there are two weak acids, two weak bases, all these are different cases, right? Okay, tell me. Now let's do next thing, that is Ostwald's dilution law. What do you mean by Ostwald's dilution law? It says that for weak electrolytes, The percentage ionization increases as concentration decreases. That now they are not talking about weak acids or bases, they are talking about weak electrolytes, right? If there is an electrolyte that is not 100% dissociated, the percentage ionization, that means the percentage of dissociation, increases as the concentration decreases. So that means when you dilute, that means when you add water, the value of alpha will increase. This is what they are saying in simple language. Percentage ionization increases as concentration decreases. That means when you dilute it. And at infinite dilution, when infinite dilution you do, when concentration becomes zero, the weak electrolyte undergoes complete ionization. That means weak electrolyte will become strong electrolyte. It will start showing 100% dissociation here. This is Ostwald's dilution law, and let's understand how this law is made, why this law is said so. Right? Okay? Yes. It's same as acidity. It's kind of same. We'll see that. Right? The way you solve it is same. Right? So it's concentration is C, this is 0, this is 0. This is the every single time we are doing this. C minus initial concentration C into alpha. Now here alpha is degree of dissociation, but this is not a strong acid or a strong base or a weak, sorry, this is not a weak acid or a weak base, this is a weak electrolyte, right? That can be acid, that can be base. This is C alpha, this is C alpha. Achha, now see one thing. Now here we are not writing Ka or Kb, we are writing Kc, that is K equilibrium. That is equals to, I'll just define it like this. K equilibrium is equals to A positive concentration, this is B negative concentration divided by AB, right? That is equals to, if A positive you have, that is C alpha, and this is also C alpha, this is divided by C minus C alpha. So this is C square alpha square divided by, this is, wait a minute, same thing, C you take common, 1 minus alpha, it will cancel, this is C alpha square. Okay, how many times we are repeating the same thing? Now see one thing, if I say alpha is, degree of dissociation is very small, right? Very small dissociation is there. If I say, if alpha is very, very, very small than 0.05, then we will write that K equilibrium is equals to C alpha square. Right? Now, see what we are going to do here. It is going to be C alpha square. Right? This all is done. Now, C alpha square we know. That means alpha is equals to K equilibrium by C. What is C? C is concentration. Do you remember molarity is equals to number of moles by volume in liter? That means molarity and volume. Molarity is a way of concentration only. And usually in all these cases, we represent molarity as concentration. So that means molarity and volume are inversely proportional. So with that, we can write it as alpha is equals to K equilibrium into volume. Right? So this is what we want to say, that as alpha decreases, that means as you increase the volume by diluting, alpha is going to increase, ionization is going to increase. It will increase so much that at one point, at infinite dilution, it will become equals to the strong electrolyte. It will be 100% dissociation. Even the weak electrolyte will start showing 100% dissociation. It is such a diluted solution that 100% dilution, even with a weak electrolyte, it is showing, right? So what they are saying, as alpha increases, with increase in dilution, decrease in concentration, at infinite dilution, alpha reaches its maximum value. Infinite dilution means what? This is going to be infinite, so this alpha also will be infinite, that is 100%, right? So from the graph, we can see here we are decreasing the concentration, we are increasing the dilution. As you increase the dilution, at one point it is increasing, alpha is increasing, and it reaches to 1, that is 100, the point of 100% dilution, 100% dissociation. The point where a weak electrolyte start behaving as a strong electrolyte. Okay, yes. Right? Tell me guys, is that clear? Is there any problem here? See, till here, I think if we are doing this like third time we have done this, right? So that won't be a problem, but this is a new thing for you, right? Okay. Then there comes a question, that is percentage of pyridine that forms pyridinium ion in this much aqueous pyridine solution. Kb for this is this, and what they are asking you, percentage of pyridine. See, pyridine is a base, so I'll say a base will accept ion and it will form, you can say this is pyridine. It is accepting the ion, it is getting H positive, it is getting converted to pyridinium ion, right? And it is giving us OH negative, right? Because it is accepting H positive. And they are saying initial concentration, the percentage of pyridine. That means if I say what I have taken, it is initially C, it is 0, it is 0. This is C minus C alpha, this is C alpha, this is C alpha. Remember one thing, they are asking the percentage of pyridine. That means that forms pyridinium ion. That means they are asking you the value of this C alpha. Which percentage out of this C is getting converted to pyridinium ion, right? So that means they are asking you the value of C alpha here, right? What is the value of C alpha? Kb is given to you, right? And initial concentration is given to you. If you remember, OH negative concentration is equals to C alpha, which is the percentage of pyridinium, which is the concentration of pyridinium ion, and this is the amount of pyridine that is being converted, right? So the value of C alpha is going to be under root of Kb into C. So under root of Kb is given to you, that is 1.7 into 10 raised power minus 9. Concentration is given to be 0.10, right? Put the value here, get the value of C alpha, and then the percentage value is going to be, C alpha divided by C multiplied by 100. So that is even simple. You just have to calculate the value of alpha here. Don't calculate C alpha. Calculate the value of alpha. Why we are calculating that? Because eventually this is going to cancel this. They are asking you alpha multiplied by 100, right? So what is the value of alpha? Tell me, how do you calculate alpha? Alpha is equals to under root of Kb by C. Because Kb is equals to C alpha square, na? So that will become Kb by C. So Kb is equals to what? 1.7 into 10 raised to power minus 9 by C is 0.10. You will cancel this, it will become 10 there, and you will calculate the value of alpha. Then this will be multiply this alpha with 100, and that you will get your answer. Okay? Focusing on understanding, listening. Meanwhile, you are just creating other topic questions. Done? Okay. So that is this one. Acha, now this is how you solve this, right? You calculate the value of alpha, then multiply it by 100, and you will get your answer, right? Okay. Now let's see ionization constant, that is Kw. What is Kw? We'll talk about that, right? Now let's understand what is Kw and all. So since water act as both acid and a base, an equilibrium exists between them. If you talk about water, there is an equilibrium that is existing between water. So water is amphoteric in nature. Do you know what is amphoteric? Amphoteric is the one that is behaving as water is amphoteric. That means it behaves as both acid and base. So what we want to say, let's say this particular molecule is behaving like an acid and this is behaving like a base. So this will donate H positive and will be converted to OH negative, and this will accept H positive and it will be converted to hydronium ion, right? The ionization constant, if you write here, will be what? Tell me, what do you write here for the ionization constant? How do you write it? You write it like this, na? You write it like this. You say, ma'am, Kw. This is called as ionization constant represented by Kw, right? That is equals to product is this divided by reactants. But these are liquids. If you see, they both are pure liquid. Pure liquid is never written in the pure liquid is never written, right? That's why this will be neglected here as, you can say, not included as it is pure liquid. Pure liquid and solids are never included, so answer is going to be Kw is equals to H3O positive multiplied by OH negative, right? And if you remember, I told you, if there is one H positive, it will get attached to one water and it will form one hydronium ion. If you have 100 H positive, it will get attached to 100 water molecules and it will form 100 hydronium ion. That means the concentration of H positive and hydronium is always going to remain the same. So you can write this over here, Kw is equals to H positive and OH negative, right? That is a very, very important formula, Kw. Now we'll understand more about Kw, that is your ionization constant. Okay. Yes, everybody, tell me. Okay. Focus, right? Kw is equals to H positive into OH negative. That is clear. What is Kw? That is ionization constant. That is equals to concentration of H positive and OH negative. Now see in detail what I am going to talk about. Since water is a pure form, so H2 is omitted. So Kw will be this. This is called ionic product, right, of water. What is this called? Ionic product of water. That is Kw. Now Kw has a constant value at constant temperature. So what we'll say, at constant temperature, value of Kw is fixed. That means, can I say, as I change the temperature, value of Kw will change, right? So if temperature is changed, Kw changes. Let's see how it changes. It increases or it decreases. Let's see. Let's talk about that, right? Let's talk about whether it increases or decreases here. Okay? Let's talk about whether too strong acid affect Kw. Ma'am, how to get slides for notes? You will get the notes in the description box, right? Okay. Tell me. So if temperature is changed, Kw will change, right? Okay. Now see, let's talk about this. So we have seen that water molecules are there. This is OH. When this H positive will be given to this will become OH negative and this will become hydronium ion. Okay, this we have already seen. Now see how it changes with the temperature, right? Firstly, I want to show you this thing, that how it changes with the temperature, right? Ionic product for water is a thermodynamic equilibrium constant. It is dependent on the temperature, right? What we can see is it is dependent on the temperature. So there is a, do you remember Clausius-Caprion equation? Clausius-Caprion equation, how many of you remember? Since the reaction of ionization of water is endothermic, we are saying the reaction is endothermic. The Kw value increases with increasing temperature. Do you remember Clausius-Caprion equation or not? Do you remember that, everybody? Do you remember that? Right? Clausius-Caprion equation is, I'll just show this here. I'll just write this here. Clausius-Caprion equation is where you have log of K2 by K1. This is delta H. This is RT. 1 by, you can write this as T2 minus T1. This is T1 into T2. And here you have negative. Do you remember this equation? Ma'am, what is temperature of Kw? Ma'am, what is temperature of Kw? Meaning? Beta, Kw is a constant, just like Ka, Kb, K equilibrium. All these are constant, na? These are types of equilibrium. If you have an acid, it is called as Ka. If you have a base, it is called as Kb. If you have two water molecules, one is losing and one is accepting H positive, right? This kind of situation, then the same equilibrium constant will be called as ionic product or ionization constant, that is Kw, right? Okay. So this is Clausius-Caprion equation. Tell me if you remember this or not, right? Right, everybody? Okay. Yes. Done. Acha, see. Now see this thing. If this is log of this, we have done this Clausius-Caprion equation in chemical equilibrium, that is log of K2 by K1 is equals to minus delta H by R 1 by T2 minus 1 by T1, that is nothing but T1 into T2 multiplied by this is T2 minus T1. That is Clausius-Caprion equation, right? Okay. In this equation, if you see in this equation, we are saying that this particular reaction where water is accepting, water is losing H positive, this is called as, this is an endothermic reaction. Endothermic means delta H is going to be positive or negative? Positive, right? Delta H is going to be positive. You put the value here. If I say this is positive, if I say this is positive, right? So I'll just write this here. If I say this is positive, This is already positive because temperature is increasing. That means T2 is greater than T1. That means T2 minus T1 is greater than 0, that it is positive. So if I say this is positive, that means overall value here is going to be negative, right? That means this overall value here is going to be negative, right? That means, can I say log of K2 by K1 is negative? If log of anything is negative, that means that anything here is less than 1. That means K2 by K1 is less than 1. That means K2 is less than K1. Right? Wait a minute. This is coming out to be negative or positive? This should be positive. This is positive, this is positive. This overall value is going to be if I'm writing here minus, then it should be K1 by K2. Otherwise, I'll have to put not minus here. So I'll not put minus here. I'll make it even simple. Let's put K2 by K1 is equals to this, right? Let's put this thing. Right. Okay? Because I am here taking T2 minus T1, na? Then I'll take K2 by K1. This will be positive here. So log of K2 by K1 delta H by R T2 minus T1. That is correct. Right? So here it will be K2 by K1. If this overall value is coming out to be positive here, if I say this overall value is positive, that means K2 by K1 is going to be greater than 1. That means K2 is greater than K1. So here I can say T2 is greater than T1, K2 is greater than K1. That means temperature is directly proportional to K, that is Kw. Right? So as temperature increases, Kw increases. Tell me, is that clear? Is that clear, everybody? Okay, tell me. Yes. Tell me. That is clear? Any problem there, right? Okay. So just remember that always, as I have told you in Lee chart layer principle as well, this I just showed you so that you know where it is coming from, right? Always remember in Lee chart layer principle, if you have endothermic, it is directly proportional. If it is exothermic, it is inversely proportional, right? And it is coming from Clausius-Caprion equation, right? You can write it like this. You can write it like this. You can write it like this. Log of K2 by K1 is equals to minus delta H by R. Then it will become T1 minus T2 by T1 into T2. Or you can write this as T2 minus T1, then this will become log of K1 by K2. Okay? Or you can remember this as it is. So in different books, you will see different things. But overall, the meaning is same. Right? Okay? Now, as you can see this over here, that temperature we have defined that why it is increasing. So if you see from the data as well, that as the temperature is increasing, the value of Kw is also increasing here, right? The Kw value increases with increasing the temperature. And if you see, this value is fixed at every temperature, and at room temperature it is defined as 10 raised to power minus 14. That means we can write it over here that the concentration of H positive has to be found out experimentally as this. Now this, let's see what exactly we want to say. I'll tell you that what exactly we want to say. You can take it in two ways, okay? You can say that at 25 degrees Celsius, Kw is equals to 10 raised to power minus 14. So you can say H positive and OH negative concentration is always going to be 10 raised to power minus 14. right? Or you can say that the concentration of H positive has been found out experimentally for pure water. This is only for this concentration, that H positive is equals to 10 raised per minus 7. This is for pure water. There is no acid, no base here. It is pure water, right? And for OH negative, it is found out to be 10 raised per minus 7. That is for pure water. So that means Kw will become 10 raised per minus 7 into 10 raised per minus 7, that is 10 raised per minus 14. And this value is defined at room temperature at 25 degree Celsius, right? Okay, this value is defined at room temperature at 25 degrees Celsius. Ma'am, what if it is not a pure water, right? That question also can be there. That also we'll talk about, that if what if there is no, yes. Yes, yes. Kw increases, more H positive, water become more acidic. I'll tell you about that, Louis, right? Actually, you can't directly say that Kw increases, then H positive will be more. I'll define that, right? First, let's focus that 25 degrees Celsius, what is happening. At 25 degrees Celsius, Kw is fixed. I'm writing at 25 degrees Celsius, Kw is always 10 raised per minus 14. For pure water, H positive concentration will be 10 raised per minus 7 and OH negative concentration will be 10 raised per minus 7, right? So H positive and OH negative concentrations are equal, right? Or you can, define it oppositely. Opposite is better. That at 25 degrees Celsius, Kw is fixed. That is 10 raised per minus 14. So for pure water, 10 raised per minus 14. So for pure water means it is not an acid, it is not a base. That means H positive, H negative concentration are equal. That means you can say 10 raised per minus 14 is equals to H positive concentration square, because both are equal, so you can write it square. So H positive concentration will be 10 raised per minus 7, that is equals to OH negative concentration. But ma'am, what if it is not a pure water and the temperature is 25 degree only? Then ma'am, what will happen? Let's talk about that. Okay. So density of water is this, molar mass is this, thus H2 at room temperature is this, that has molar mass 55.55 molar, that you can remember for your numerical, right? This data you can remember for numericals. Acha, see next one. Now we are saying that ionic product concept is applicable to pure water and to any aqueous solution. I am not saying always to pure water. To acidic solution, basic solution also it is applicable. Let's talk about how it will be applicable. But if you talk about pure water, because these concentrations are same, that is why H positive, OH negative concentrations are same here. But in other solutions, they will not be equal. As the concentration one of these ions increases, the concentration of other must decrease. What do you mean by that? Let's talk about this thing, right? So if I talk about this, so I've already told you, instead of this, let's talk about defining acid, base and neutral solution. See, I'll divide into 3 categories, okay? 3 categories. At 25 degrees Celsius, Kw is fixed, that is 10 raised per minus 14. There is no doubt in that. 25 degrees Celsius, Kw is fixed. There is no doubt in that Kw will change at a constant temperature, not at all, right? So I can write first is a acidic solution, then there is a neutral solution, then there is a basic solution, right? Now, if you see this here, in all the cases, in an acidic solution, H positive concentration will be greater than OH negative, only then, because if H positive is more, only then it is going to be acidic. In neutral solution, H positive concentration is equals to OH negative. In the basic solution, H positive concentration will be less than OH negative, right? But we know one thing, that Kw is also the same, always the same. So you can write one thing constant here, that H positive multiplied by OH negative is always 10 raised to power minus 14, no matter what. H positive multiplied by OH negative is here also 10 raised to power minus 14, because we are talking about 25 degrees Celsius. Here also H positive and OH negative is going to be 10 raised to power minus 14. So it is fixed. It is not changing. The concentration is not changing, right? Concentration, I am saying the Kw value is not changing. If I say here this value has increased, now to make this overall thing constant, this must decrease. This must decrease. Oh, yes, this must decrease. See, if I say overall value has to be 12, either you write 6 into 2 or you write 3 into 4. It is going to be 12 only. But if I say here this value has increased, then this value has decreased here. Okay. So to make the multiplication constant, if one value is increasing, other value has to decrease, right? Okay. So that is the reason here we know that both are equal. That means this is also 10 raised to power minus 7. This is also 10 raised to power minus 7. Here we are saying that if this value is decreasing, or you can just simply say if this OH negative is increasing, right, because it's a basic solution, then this will decrease, because overall we want it to be constant. So that means, can we say one thing, that here H positive concentration will be greater than 10 raised to power minus 7, because it is increasing, and OH negative will be less than 10 raised to power minus 7. Here H positive and OH negative are equal to 10 raised to power minus 7. And in this case, we can say, because OH negative is increasing, that means OH negative concentration is, that means we can write this over here, OH negative concentration is greater than 10 raised to power minus 7, and H positive concentration is less than 10 raised to power minus 7. Got it? Right, everybody? Tell me. Is that clear? Right? So this is not changing. Kw is not changing here. Right? So we can say for an acidic, H positive is greater, OH negative is less. Neutral, both are same. Basic, H positive is less, OH negative is greater. Right? Tell me. Clear? Clear, everybody? Now let's see the next thing. That is calculate the concentration of H positive in a solution in which OH negative is this at this, a solution in which OH negative is this at this, Kw for water at this, and 30 degree and 25 degrees are given respectively. So first we will solve for A part, then for B part, right? First we will solve for A part, then for B part. What is this A part? That says a concentration of H positive, a solution in which OH negative is this, at 25 degrees Celsius. Now, see this. OH negative is given to be 0.010 molar, right? Concentration is given to you. See, we know that H positive into OH negative is going to be 10 raised to power minus 14 at 10 raised at 25. In the B part, H positive and OH negative is going to be Kw, that is 1.8 into 10 raised to power minus 9. Okay. Now, if you put the value, if you want to solve the value of H positive, so here it will be 10 raised to power minus 14 divided by 10 raised to power minus 14 divided by OH negative concentration is 0.01, that is 10 raised to power minus 2. Okay, here it is 1.8 into 10 raised to power minus 9 and OH negative is given to be, wait a minute, Kw is given to be here 14. So sorry, this was given to be 1.10 raised to power minus 14. This is 1.8 into 10 raised to power minus 9. Okay, this is 14 and this is 9. Okay, then this will be cancelled. This will be 10 raised to power minus 5, right? And this is going to be, H positive is there. That is going to be 10 raised to power minus 12, right? Okay. Tell me, is that clear? Huh? Simple, simple. Nothing big here, right? Okay. So that we have done already. So next thing is going to be what? pH scale and pH calculations. Now let's talk about pH scale and pH calculations here. Till now you have understood the value of that H positive into OH negative is Kw, right? Kw will vary with temperature. So hydronium ion concentration, if you see, have I defined P of anything is equals to minus log of that anything. Same thing. P of H is equals to minus log of H positive ions. P of OH is equals to minus log of OH negative ions. That is the same thing, right? So these two are so simple that we have done before as well. For pKa, like you have pKb. Similarly, you have pH. That is same. P of anything is equals to minus log of that anything, as simple as that. Now, if I say, example is for pure water at 25 degrees Celsius, H positive concentration is this. But I told you, whenever they have given H positive, whenever they have given X is equals to 10 raised to power minus, sorry, A is equals to 10 raised to power minus X, then P of A is equals to X. So H is given to be 10 raised to power minus 7. So this 7 is going to be the pH. Right? Or you can just solve this as well. Take log of minus log of 10 raised to power minus 7. Minus of minus 7 log base 10 of 10 is 1. So it will become 7. Right? Okay. Now let's calculate one thing based on the analysis we did earlier. This is a very interesting point. For acidic solution, have we defined that H positive concentration should be greater than 10 raised to power minus 7? This is all I am talking about at 25 degrees Celsius. I am not moving to some other temperature. I am talking about 25 degrees Celsius everywhere, right? So if for an acidic solution, H positive concentration is 10 raised to power minus 7. As H positive concentration increases, the value of pH value decreases. How? Because this P of anything is inversely proportional to, if you have P of X, it is always inversely proportional to X. We have seen this in pK is inversely proportional to K. We have seen this in pKb is inversely proportional to Kb. Similarly, pH is inversely proportional to H positive. Similarly, POH is inversely proportional to OH negative, right? Okay. So that means they are saying that, can we say H positive concentration is greater than 10 raised to power minus 7. That means as H positive concentration increases, pH value decreases, right? Thus, for an acidic solution, pH is less than 7. That is why for 25 degrees Celsius, at 7 you have neutral. Before 7 you have acidic. After 7, 7 to 14 you have basic. Right? Because for basic solution, H positive concentration is less than 7. Less than 7 means pH has to be greater than 7. And for this, write it down over here that pH is inversely proportional to H positive ion. If H positive ion is increasing, pH is decreasing. Okay? Right, everybody? This leads to the development of a scale known as pH scale, which can predict the nature of the solution. So if you see, this is the pH scale. Wait a minute, I don't know if you're able to see this or not. Give me a second. Yes. Oof. See, this is acidic. Before 7 it's acidic, after 7 it's basic, at 7 it's neutral. And this is at 25 degrees Celsius. This pH that you usually say pH, if Kw is temperature dependent, pH will also be temperature dependent. Right? I'll tell you also the reason behind that. Let's talk about another thing, right? This one, let's talk about this one. Okay. Let's talk about this one. How, ma'am? How you can say that? You have Kw, H positive, OH negative. I'm saying take log on both sides. You take log on both sides. This is log of Kw is equals to log of H positive and OH negative. Whenever two multiplications are in the log, you will add them. So log of Kw is equals to log of H positive plus log of OH negative. Right? Now take negative on both sides. Take negative on both sides. That means multiply both sides with negative. This will become minus of log Kw minus of log H positive minus of log OH negative. And haven't I told you, minus of log of anything is equals to P of that thing. So this will be P Kw is equals to PH plus POH. That is the formula. So we can write at 25 degrees Celsius. So as temperature changes, Kw changes, right? So we say, and that is the reason pKw will change. At 25 degrees Celsius, Kw is equals to 10 raised to power minus 14. So pKw is equals to 14 here. So we can say pH plus POH is equals to 14. This is that very famous equation that you have seen in earlier classes as well, right? pH plus POH is equals to 14, right? And this is the scale, this scale that you are defining here now, this scale that you are defining, if you see this scale is using 0 to 14. So this scale is using this pH is equals to pH plus POH is equals to 14. This scale is using this thing here. Okay? This scale is using this thing here. Got it? Understood everybody? Tell me. Right? So you can see this over here, that effect of temperature on pH scale. What is the effect of temperature on the pH scale? At 62 degrees Celsius, Kw is 10 raised to power minus 30. So that means the value of pH plus pOH is going to be 30. The scale is going to be half of it, right? That means the scale is going to be 13 by 2, that is neutral, you can say neutral position is going to be half of it, that is 13 by 2, that is 6.5. So it will be neutral at half of what thing you have here. Then for a neutral solution, and also we know that from a neutral solution H positive is equals to OH negative, right? So you can say that if H positive is equals to OH negative for a neutral solution, how do you calculate this? Okay? See, if I am saying H positive is equals to OH negative, you can say H positive square is equals to 10 raised to power minus 13. So H positive is equals to 10 raised to power minus 13 by 2, that is 10 raised to power minus 6.5. So if H positive is this, it means pH is going to be 6.5. Okay? pH is going to be 6.5. That means the pH scale is total 0 to 30. Right, everybody? Tell me. Is that clear? Any problem? 14 is not fixed. That's what I'm telling you, na? That Kw is changing. And if you see this particular definition here, it is pH plus pOH is equals to pKw. If Kw is changes, if Kw changes with temperature, then pKw also changes, right? So that's why here you will see the change, right? Okay. Tell me. Right? Done? Acha, now tell me one thing, that do you want to do pH calculations today, or do you want to do pH calculations in the next class? Tell me. Do you want to do pH calculations today or in the next class? Because I was thinking to complete this chapter in 2 days. If you want it, then we can do pH calculations in the next class. Then in the further little bit we can do buffer solutions, right? Then in the third class we can do solubility and solubility, salt hydrolysis, all of that thing. Tell me. Yes. Ma'am, as you want. I am thinking to do a little bit, है ना? I'm thinking the flow, if it is there, so let's do a little bit, because eventually you have your next class at 9 only. So I think we can do for strong acid, strong bases, weak acid, weak bases, and a little bit we can do, right? Okay, we can start doing that. Okay, done? Let's do a little bit, right? If you get tired in between, so we'll do, right? Okay. So, pH calculations for strong acids, right? Strong acids, that means which are 100% dissociated. Now, in this case, you will have a different way. For example, this is C, this is 0, this is 0 initially. Now, at equilibrium, all of this will be converted to C. So, this will also be C, this will also be C. So, is there any alpha? Alpha is 1 here, it is 100% dissociated. So alpha is equals to 1 in this case, right? Alpha is 100% associated. So here all of this will be completed. And if here you have, let's say, B is actually the basicity here. B is the basicity. B is the basicity. That how many H positive ions are given by an acid. For example, HCl gives you 1 H positive, H2SO4 gives you 2 H positive, right? So this is the basicity that we are defining. So if you see, this is all of this is completed. So it is C minus C alpha only. This is also C alpha, this is also C alpha. Let me make it very easy for you. But here alpha is equals to 1. So this will become C, this will become C, this will become C minus C, that will become 0. That's why directly I have written it as, right? Because all of this will be consumed. This will become C, this will become C. And always this is multi. Do you remember what I told you? That whenever this is C minus C alpha, this will become C alpha into stoichiometry here. This will become C alpha into stoichiometry, that is 1, right? Alpha is here equals to 1, so you will write BC here. This is C, and this is alpha is 1, so this will become 0. Right? This is the equilibrium concentrations. If you write the value of Ka now, or we are just calculating the value of pH now. So let's write that. What is the H positive concentration? H positive concentration is basicity multiplied by initial concentration of acid. So what is the value of pH? pH is equals to minus log of H positive of that solution. So here this is the H positive of solution. Okay? Okay, this is the H positive of the solution. H positive of solution, we have here basicity into initial concentration of the acid, right? Acha, listen one thing here. In this case now, one very important thing you need to understand, that is, this so we have seen basicity into concentration of an acid, but one very important thing you need to understand here, that is, this expression is valid only when H positive ion concentration is between 1 molar to 10 raised to power minus 6. For concentrations greater than 1 molar, activity coefficients are required. So what do you mean by that? Let's understand. If I say you have a concentration of water, now pure water will always give you how much H positive? It will always give you 10 raised to power minus 7 H positive. This is from water. This is from water. So there are two cases of acids that are possible. Two cases means, if I say an acid, its H positive concentration is between 1 to 10 raised to power minus 6. That means it is greater than 10 raised to power minus 6, right? Or if I say greater than 1 molar, so I am not even talking about. I am saying it is greater than 10 raised to power minus 6 means if its H positive concentration is lying between 10 raised to power minus 6 to 1 molar, right? If it is this, and if its H positive concentration is lying greater than less than 10 raised to power minus 6, right? These two cases are there. These two cases are there. This you can ignore because greater than 1 molar, so we are not talking about this now. Just remember that two cases are possible. Either H positive concentration will be 10 raised to power minus 6 to 1, or it can be less than, right? If you see it on a number line, let me define a number line for you, right? If you see it on a number line, then if I say, if the concentration of H positive is This is 10 raised per minus, this is 10 raised per minus 6. This is 1 mole. If it is greater, at 10 H positive is greater than 10 raised per minus 6, or here beyond this if it is less than 10 raised per minus 6. What you will do in these two cases? See, if your concentration is very high, if acid is, its concentration is very high, it's greater than 10 raised per minus 6, so you're like, hey water, I don't care about you, who are you in front of me, you have 10 raised per minus 7, I also have 10 raised per minus 6, so I'm going to ignore you, right? So if it has concentration greater than 10 raised per minus 6, it is going to ignore water, right? So ignore H positive from water. Okay. Here in this case, include water, include H positive from water. Include, because you are like, I have less than 10 raised to power minus 6, so I need water, right? Water has 10 raised to power minus 7 concentration, I need it. So include H positive concentration from water. That means the H positive solution here will be 10 raised to power minus 7, that is from water, plus H positive of acid, right? This will become the basis here, this will become H positive here, right? And here H positive will be, and here H positive will be simply, here H positive of solution will be only H positive of acid. Okay? Here H positive will be only H positive from acid. We have written the opposite here. We have written the opposite here. It is not supposed to be that. Wait a minute. Wait a minute. See. So here H positive will be ignored now because it is less. So here H positive will be H positive from only the acid, and here H positive will be, H positive of solution will be H positive from acid whatsoever it is, plus 10 raised per minus 7, that is from water. Okay, plus 10 raised per minus 7, that is from water. So these two things are very, very important for you, right? Because students usually tend to do mistake here. They don't know if to ignore H positive from water or not. That is the reason, if you see here, I would not write the pH value. Just remember that this is nothing but this is just the H positive from acid. This is how you calculate the H positive from acid. This is how you calculate the H positive from the acid. That's it. Okay. Then what is the value of pH? Ma'am, what is the value of pH? Just remember, pH is equals to whatever is this. pH is equals to minus log of H positive of solution. Now we don't know whether H positive of solution will include or will not include. That depends upon the concentration of the acid. Okay. Right? Tell me. Yes. देखो बच्चा, this is actually this particular session is actually for JEE 2027 aspirants as well, and this is basically so that we can make your concepts very strong. Even for JEE 2026 aspirants, you can watch this, but if you're looking for PYQs and marathons will come up with the next week, right? But ionic equilibrium I'll be doing only this way, right? In detail I'll do this way only. Yes, there will be short lectures as well, there will be PYQ sessions as well, but in that don't expect this much detail. Now I am literally writing everything in detail, okay? So if you're here, if you think that your ionic equilibrium is weak, ma'am, I want to core conceptual knowledge I need, then see this, right? Okay, it's because every single thing I am telling you in detail here, right? Okay, now I'll be taking one example here, two examples here. If you see these kind of questions are asked to you, I'll take one example of when H positive from acid is given to be, they have given you have H2SO4 and H positive concentration from acid is, H positive concentration of acid is 10 raised to power minus 2. Let's see, here they have given HCl. Here H positive concentration is 10 raised to power minus 9. Okay. Now, in this case, what is the H positive concentration from the acid? Acid, I told you, H positive concentration from the acid is equals to basicity multiplied by the initial concentration. है ना? Actually, this is not H positive concentration. You take initial concentration as 10 raised to power minus 2. Here also you take initial concentration as 10 raised to power minus 9. Okay. See, H positive concentration from an acid will be equals to basicity, that is 2H positive are given here and concentration is this, that is H positive. If you see this value is greater or less, this value is nothing but 0.02. This value is definitely greater than 10 raised to power greater than 10 raised to power minus 7. So whenever it is that, ignore H positive from water. So you can say that H positive of solution is equals to H positive from acid, that is 2 into 10 raised to power minus 2. So pH is equals to minus log of 2 into 10 raised to power minus 2. So minus log of 2 minus minus, this will become plus of 2. This is 2 minus 0.301. Solve it and you will get your answer. Okay. Okay. See, here H positive from acid is going to be what? Here this is going to be acidity, basicity, that is 1 into 10 raised to power 9, that is 10 raised to power minus 9, which is definitely less than 10 raised to power minus 7. So we can say now you need to add H positive from water. So what you will say, here it is H positive of solution is equals to H positive of acid plus 10 raised to power minus 7, that is H positive from water, and this is going to be 10 raised to power minus 9 plus 10 raised to power minus 7. This is H positive solution, and then just take the value of pH is equals to minus log of H positive of solution. Solve this, do the calculation, and you will get your answer. Okay, that is how your answer can change, right? Now you should be clear that where to add H positive from water and where not to add. Firstly, and also after multiplying it with the basicity, then see if the H positive concentration is greater or less, right? Okay, understood? Tell me guys if any problem you have here. On the similar basis you will have for strong bases, right? On the similar lines you will have for strong bases. Okay. On the similar lines, you will have for strong bases. Okay, tell me one thing. What is A here? A is the acidity. Okay, I think there it is defined wrong. It should be B written here. It should be B. It is written N factor. We have taken B as the basicity, no? So it should be written B. Okay. Now, same thing, repetition of the same thing we'll do here. It is the repetition now. Let's see what will happen. Right? Yes, ma'am, no problem. Great, Shri, Durga, Sparky. Varun, Achu, Louis. Water contributes H positive at low acid concentration. Definitely correct, Louis. Very good. Definitely at low acid concentration, it is defined that is 10 raised per minus 6. It should be greater or less than 10 raised per minus 6. Okay. Yes. Now let's talk about pH equal to minus log concentration of all concentration and temperature. Sorry, I didn't get you. If strong acid dissociate 100%, why they don't give pH equal to minus log concentration of all the concentration? They are giving acid is though giving acid, though I am including only here. Where I am not including acid concentration, here also it is included, here also included. Water concentration we are thinking. Sometimes the acid concentration is so large here that we don't add the concentration of water here, right? Okay. Yes. If you see this here, now from the strong base it is same. This is concentration initially 0. This is this C, it is 0 0. It is C minus C alpha. This will become C alpha into unity. This will become C alpha into A, right? As alpha is equals to 1, as alpha is equals to 1 for strong base, same I am doing, strong base. So this will become equals to 0. This will become equals to C. This will become equals to AC. Right? So can I say the OH negative concentration is what? And this is from base. I am saying all of it is calculable. In this case also I have said beta. If you see this over here, this case also, yes. This case also I have told you that all the concentration is getting dissociated. So that's why H positive from acid is this. On the similar line, all the base is dissociated. So OH negative from base is acidity multiplied by initial concentration. Okay, that is OH negative concentration, right? That is going to be OH negative concentration. Now, same thing that we did in case of water, in case of acid, same thing we are going to do here. Same. Not even a 1% difference is there, right? So, two cases we'll have. What are these two cases? Either, ma'am, OH negative concentration can be greater than 10 raised per minus 6 or it can be less than 10 raised per minus 6. Okay. If I am saying that it is greater, I am not talking about concentrations greater than 1 molar. Okay. So it should, even if it is greater than 10 raised per minus 6, that means it can maximum be 1 molar. Okay. Greater than 1, though we are not talking about that case only, right? We'll talk about that, but now we are not talking, right? So here, shall we ignore or what? In this case, what we will do? If your concentration is very high, you will ignore water. You will be like, water, go to hell. We don't care, right? You will ignore. Acha, tell me one thing. If you get into IIT, will you look at NIT? Or if you get into NIT, will you look at any private college? If you get into really good private college, will you look at some random private college? No. It depends upon what you are getting. You will ignore what you don't want. Right? Okay? So, ignore OH negative from water. Here you have to include OH negative from water. So that means what we are doing here, we are simply writing OH negative of solution. Okay, I'm always writing solution here, and you will see I'll write throughout solution only. I will never write acid or base. I'll write solution. Okay, because if you see this here also I have told you the pH value is minus log of H positive solution, right? So it is minus log minus OH of solution. This is H, this is OH negative from base. That's it. And here it will be OH negative of solution is equals to OH negative from base plus 10 raised to power minus 7. Now, in both the cases, what is the value of pH? If it's very low, then very low nahi. I'm defining it should be less than 10 raised to power minus 6. Randomly, you can't say. Scientists have defined it that it should be less than this, then you will include. If it is greater than this, then you will not include. They have given that point where you will see that whether it's less than that or greater than that. Okay? Yes. Done? Acha, now see, what is the value of pH? Sorry, POH. Because you're calculating pH, so it will be POH, that is minus log of base 10 OH negative of solution. As all these things that we are doing, it is at 25 degree only. If nothing is mentioned, especially they mention that it is not at 25 degree. Usually in these kind of numericals, they will not do that, right? They will, if they have specially mentioned the temperature, then you will think about that P, KW will be different, but otherwise it will be 14 only, right? So we'll write pH is equals to 14 minus POH, right? Okay. Tell me, is that clear? Is that clear, students? Right? Is that clear? Okay. That is done. Right? Tell me, if there any problem in this particular thing, this though I have already defined, right? So, chalo. Okay. Now, two strong acids and two strong bases, right? 3 more will do, and rest of it will do in the next class. Or do you want to finish this? So we'll do it in the next class then, okay? We'll do it in the next class, right? Or we can do actually, we can do pH of strong acid, strong bases, and one strong acid, because that is very simple. Trust me. You believe in me, na? Trust me, that is very simple. Two strong acid, two strong bases, and one strong acid and one strong base. That is very simple. But yes, then the combination of one strong acid, one weak acid, that again calculative it is. But these three combinations are very simple and they are very much asked, right? Okay. So last one, last three. I promise that is last three. I promise, right? Okay. See, when strong acid is dissolved in water, the following equilibria are established, right? This is strong acid and this is water, which is giving you H positive and OH negative. Acha, this is the very dilute solution, na? Huh. This also we have done. So this is common to both the substances. The contribution of H positive ion will form from both this and this. Beta, this all we have done, okay? We have done this. It's just that what I have told you there in the form of this chart, it is written in the form of theory, okay? So it is written in the form of theory, right? Okay, let's do this question. The pH of this much of NaOH solution will be what? The pH of this much NaOH solution. See, if you see this, OH negative from the base is equals to basicity is 1 because it is giving you only 1 OH. It is 10 raised power minus 2, which is definitely greater than 10 raised power minus 6. So you will ignore pH of solution is equals to, sorry, OH of solution is equals to OH from the base. So POH is equals to minus log of OH of solution, that is going to be minus log of OH negative of solution is what? That is 10 raised to power minus 2, that is going to be 2. So pH is going to be 14 minus 2, that is 12. So answer is going to be C is the correct answer here, okay? Got it? Yes. Weak acids, yeah, I don't want to do it. Weak acids, I wanted to do 2 strong acids and 2 strong bases. Okay, till here, till 61st slide will complete. After that, trust me, I will end the class, right? So pH of 2 strong acid, very small amount we are left with, very small, right? So we'll do it fast, right? Let's not even my throat is paining, but let's do this, you know, let's do this. Otherwise the second class, the next lecture is going to be very lengthy. I want to cover buffer solution there. Buffer solution itself is a very big topic. I want to cover this, then the question on this. So it is going to be a very like 3-hour lecture. So it will become difficult for you. So let's do at least this much so that lecture less thing is there. Okay. pH of mixture of 2 acids. So in this case, N is the normality, V is the volume, M is the molarity. Always remember N1 is equals to N factor of 1 into molarity of 1. N2 is equals to N factor of 2 molarity of 2. Right? N factor is the number of H positive given, the number of OH negative given. Right? So for the acid it is N1V1, for the acid 2 it is N2V2. Whenever you have 2 acids, the total H positive of the solution will be addition of N1V1 plus, and very simple, N2V2 divided by V1 plus V2. That's it. It's done. So it will be M1 into N factor of 1 V1 plus N2 into N factor of 2 V2. So they have written N factor as N1 and N2 only, right? So I will write N1 and N2 only. This is N1 M1, this is N2 M2. Okay? So this also I'll define it as N1 M1 V1 N2 M2 V2 divided by V1 plus V2, and that is your H positive of solution. You are given with 2 acids, you simply do this. This is such a simple thing. You do this, molarity or normality will be given to you. Then pH is equals to minus log of H positive of this solution. That's it. Simple, right? This is not complicated. This is simple. Similarly, in case of 2 bases, in case of bases, you will calculate OH negative of the solution. Here, OH negative of the solution will be N1 again. If you have 2 strong bases, it will again be added. N1 V1 N2 V2 divided by V1 plus V2. This will become N factor of 1 M1 V1 plus N factor of 2 M2 V2 divided by V1 plus V2. That's it. That's it. But remember that this is OH negative they are talking about. This is OH negative that they are talking about. They are not talking about H positive. So you'll calculate the value of OH here, that is minus log of OH negative of solution. Then you will say pH is equals to 14 minus POH. And that will be your answer here. Tell me. Clear? Okay. Right. Now, see this. This one is very important. Here, things will change because you have an acid and you have a base, right? When you have an acid and you have a base, then things are going to change here. How? Let's say I have acid which is giving me 15H positive. This is giving me 20 OH negative. That means OH negative is concentration is greater. Now out of this, in neutral, you will be left with only 5 OH negative. Rest of them, that means it is going to be a basic solution. Because 15H positive and 15 OH negative will be neutralized and will be left with only OH negative. If I say the opposite, if I say you have 25 H positive, you have 20 OH negative. 20 will be neutralized, 5 H positive will be there. This is going to be a acidic solution. You will calculate pH of this solution, right? Okay, so based on these two things, we are writing it that there will be neutralization of acid and base. The solution will be acidic or basic depending upon the component that is taken in excess, right? So if you see this here, case 1 is if N1V1, that is acid, is greater than base, because acid I am defining, if you see this, for acid I am defining N1V1 and for base I am defining N2V2. If I am saying N1V1 is greater than base, that means acid is greater than base, then H positive calculation will be there. And here always remember, if you calculate H positive or you calculate OH negative, it will be large minus small divided by V1 plus V2, right? Or you can say NV, whatever NV value is large minus whatever NV value is small divided by V1 plus V2, both the volume. And H positive you will calculate when it is, when N1V1 is greater than N2V2. This you will calculate when N2V2 is greater than N1V1. Okay. So if acid is more, so it is acidic, N1V1 minus N2V2 by V1 plus V2. If basic is more, if I say this is acid, this is a base. If I say base is more, then N2, then you can say N2V2, this larger will be subtracted from the smaller divided by V1 plus V2, right? And this is the value of solution OH negative and this. Here what you will do, you will directly calculate pH is equals to minus log of so many times. Here minus log of H positive of solution, OH negative of solution, or pH is equals to 14 minus POH. Okay. Tell me, is that clear? Is that clear? Done, everyone? Okay. Done. So yeah, now I'll take your leave, right? Rest of the things we'll do in the next class, right? rest of the things, and this is your homework. Conjugate base for bronzed acid H2O and HF is going to be what? Conjugate base means after losing H positive, it will become what? Right? Okay, chalo. Okay then guys, that's it for today, and I'll see you all in the next class. And before going, let me remind you about the test series here, right? And also, firstly, let me remind you about the ma'am, where I will get PDF. So many times you have asked the same question, right? So if you see this over here, ask with any doubts, click on there, you will get the PDF of the session. You can ask any doubt related to the session over here, right? Any doubt you have, you can ask your doubts over here. Second is rank booster test series for all the JEE 2026 aspirants. Guys, in this, what you will get is 11 part test, 25 full test, and 3 hour each. You will get that 75 question each. And moreover, you will get 93 weightage topics, 93 high weightage topic test provided in unscheduled format, so that you can attempt them anytime. So these are different 93 tests, that is topic wise test. So you can study your topic, let's say, and these are not scheduled. They are already there. You can, let's say today you are studying this ionic equilibrium. Take out the test of ionic equilibrium and do that test. Okay, it's like that, right? And here only important topics are there. And in this, these are part syllabus, half syllabus, and these are full syllabus test, right? Okay. And this, if you see that what is the price, then you will be shocked. It is only 999, where we are providing you all these things, right? So the link is in the description box. Go and purchase that, because at 999 you're getting these many things, and the video solutions for these test series are also available, right? Okay, right? So guys, that's it. Now I'll see you in the next class. Till then, bye bye, take care, bye bye.